We are going to talk about ARC, which is automatic reference counting, or ARC as many people call it. The question here is that how does these objects which keep getting created by Xcode eventually get reclaimed? So in a sample example, we have a simple code that is written. We have a couple of classes, customer and address, and we are trying to simulate, for example, a cart. And in the cart scenario, I have a customer name and it's linked to an address. Now, in my code, all I'm doing is that I will write some pieces of code and then I will go forward and instantiate address and customer. Then I write some more pieces of code and do the same exercise again, and eventually I do some more pieces of code, some cleanup, and finally refer address and customer, but then I'm done. The thing is, if we just keep referring to the objects and we keep on building those objects again and again, like you can see here, do something has been called thrice, line number 31, 34, and 37. And if address and customers keeps building again and again, the memory footprint, and I'm gonna draw a chart here saying that, okay, this is my time and this is my memory footprint. So my with time, my memory footprint will just keep on increasing because, well, I'm creating more and more objects, and each object requires some memory. And eventually, I'm going to run out of memory on my device, and my app is going to crash. So why doesn't the apps crash? And there are so many apps out there that use tons of memory. They capture images, do video streaming, but they don't really crash. So what's happening? What's happening behind the scenes is that once you refer the objects, and again I'm going to take an example of do something where we're referring to address and customer. So let's say that this is my address and this is my memory location where the actual memory is allocated to store the address and the customer objects. Now I have variables, and the variables, which may be called as address and customer itself, point to the memory location. So as you know, objects are passed by reference, not really by value. So each object contains a reference to the location where the information about the object is actually stored. So these are references that are maintained. And of course, you can actually do something like b equal a, and now b is also a reference to a. So the references can keep pointing to the same location in memory, and you can keep getting back the same data. But the thing is, when is this memory getting reclaimed? Now let's look at this example again. Line number 31, we call do something. It goes in and calls the address, instantiates the address object, and now address is pointing to the address memory location. Line number 26, customer is pointing to the customer object. All good and dandy. Line number 27, we go forward and print those values. Now after line number 28, we are actually exiting the function. Internally, what's happening is that the OS itself is maintaining a reference count. And what it's doing is that once the variable a got into the picture, it now has a reference to the memory footprint which is allocated for a and is pointing there. But eventually, when you reach line number 27, after line number 27, line number 28, the reference is now going to go away. So the OS is keeping track and saying that, well, now there is no reference that is pointing to this memory or this portion of the memory. So as a result, this memory is now available to be reclaimed. The OS is not going to go ahead and immediately reclaim the memory. So it's not like line number 28 approaches and suddenly the memory is available. But this memory is now available to be reclaimed by the operating system whenever it desires to. OS for optimization purposes will of course run it asynchronously, and at some point in future decide that it is the right time to reclaim the memory and go forward and reclaim the memory. The important thing is that once the references are gone, the object is now available to be reclaimed by the OS for cleaning up. Now, if we provides circular references that A is pointing to another variable which is pointing back to A. As a result, there's always a reference pointing to each other. That's called a circular reference. So let's say there are two objects A and B. A points to B, B points to A. As a result, there's always be an object pointing to each other, and for these, the memory cannot be reclaimed, and that's the situation where you hear the word memory leak. But for all other objects, as long as the references are removed, the OS is free to go forward and reclaim the memory, and hence the memory buildup can be stopped. And once the OS triggers in the function to clear the memory, you can see that it will have a step function where the memory used by your app will decrease. Now, there are other variations to this. For example, I'm talking about variables and constants, but if you define something as static, then yes, it's going to always live and it's never going to be reclaimed. So statics are generally bad from memory perspective. Um, if you go back a few years before ARC was present, what used to happen was you have to actually call functions like malloc and deloc to actually allocate memory and deallocate the memory. And ARC was a big step in making the life simpler for the developers, because now as a developer, you just want to make sure that you are not doing circular references. And as long as you are meeting the criteria, not doing circular references, the OS will take care of cleaning up all the memory for you. And that's all there is to know for ARC.